So good morning, afternoon, based on your time zone, everyone. My name is Victoria da Poian. I am a French aerospace engineer working at NASA Goddard Space Flight Center in Maryland in the United States. So I am part of the Planetary Environment Laboratory that mainly studies the chemistry and the astrobiology of atmospheres and surfaces of planetary bodies. So in my department, we build scientific instruments and we send them in the solar system to look for life and to understand of the planets and the solar system itself. So today I will talk about artificial intelligence and machine learning for NASA planetary missions. So I will first mention the goals for exploration missions to just give you an overview, then give you also an overview of the challenges of missions operations, and I will dig into the concept of science autonomy, that is mainly my main research focus at NASA. And to illustrate this science autonomy concept, I will describe one study case I've been leading on one instrument that will be delivered to Mars in 2023, hopefully. And to conclude, I will mention other projects where machine learning and planetary science collide to answer scientific questions and also some challenges that we have to face. So first, why NASA and other space agencies want to explore the solar system? So the main goals of the explorations of the solar system are mainly to understand the formation and also the evolution of the solar system, to understand if there is possible life elsewhere, a life that will be different than the one we have on Earth, and also the different environments and processes that we can find in our solar system. So here I just put some of the main interesting targets of our solar system, such as Mars, the Moon, the other Saturn and Jupiter, but also the moons of these planets like Enceladus, Titan, Europa, and other interesting targets. So just to give you an overview on this next slide, you can see the solar system, and I wanted to show you different missions the department I'm working with has sent missions to. So here you can see the name of the mission, Cassini-Huygens, and a picture of the spacecraft and a picture of the instrument that the department I'm working with at NASA built. So Cassini-Huygens, which explored Saturn and the environment around, but also missions to Mars with Curiosity missions, and MAVEN. MAVEN studied the atmosphere of Mars, but also future missions with Mars 2020 that has been launched in 2020 in July, and that will get to Mars in 2021, and ExoMars mission I will describe later that is supposed to be launched in 2022. So also other missions going to Europa and to Dragonfly. So Dragonfly is really cool. It's a kind of drone that is going to explore Titan, that will explore the surface of Titan, but also the atmosphere. So really interesting mission that NASA selected last year. So all of these missions require a big team working on the real-time operations. And in this section, I want to give you an overview of the complexity of the missions, the operations, and the planning of all these scientific missions. So to give you an overview, I wanted to use Mars mission, the Curiosity mission on Mars, that is operated by a large team on the Earth. And we can describe the operation cycle with 3 big steps. So hopefully you see my screen and my cursor. So here on Earth, we have the science team that define the experiments that we want to run on Mars. And they send the experiment to Mars with a software. And when it's done, when the experiment is achieved, data is sent back to Earth and processed by a specific team that has to verify and to convert all the data to a usable format. And when it's done, they send back the data to all the international teams that we have around the Earth for the data analysis process. And we do this over and over around for months, sometimes years. So yeah, that's just the cycle. And for you to understand what is the challenge for space operations, I want to compare the Mars mission and the other planets we want to go to explore. And to think about this, Mars, in fact, we are really lucky because we have satellites around Mars that are used as relay to transmit the data to Earth. And so the time to go back, for data to go back to Earth is really short. And the majority of planetary missions return only one thing. It is data. So we really want all that matters right now is data. And the lifetime of missions on Mars are usually longer than the one on Europa, Enceladus, and Titan. So around months/years on Mars, and weeks and months, or just days sometimes on Europa. So we want to be sure that we receive all the data, the science data that the satellites and the spacecraft will get from these planetary bodies. So because we want to go further in our solar system, the time required for data download, data sampling increases with distance. So we want to be sure that we develop a model that is different from the Mars model for further bodies like Europa, Enceladus, and Titan. So here you can have an idea of the different planets of our solar system. There is not all the moons, but Mars, in fact, is really, really, really close to the Earth. So when we want to go further to Saturn, Jupiter, and we send all these billion-dollar spacecraft, and they only return data, we want to be sure that we get all the data from the spacecraft. And also because all these missions and the ambitions of these missions are growing, the development of new instruments enable to generate more and more data. So the operations model we have on Mars right now with humans in the loop that makes decision will not be possible for short duration mission going further in our solar system. So this is all the reasons why we need to maximize the value of each bit. And to do this, we need the instruments that we send on the spacecraft to be more selective and smarter. That's why we developed the concept of science autonomy on board that I will describe in the next session. So this science autonomy concept combines space science and artificial intelligence and machine learning. So this is clear that the space science community will need more autonomy for flight instruments and software in order to achieve all these amazing goals NASA and space agencies want to work on. So the very long-term goal is to maximize the value of each bit. So we envision instruments that will be able to analyze the science data on board, and so they will be able to adjust themselves to run the next operation without having the humans in the loop, and be able to transmit Earth only the most interesting or timed critical data. So this is really, really optimistic. It's a long-term goal, as I said. So we first started with a shorter-term goal with only a support on Earth. So the idea is to develop a proof of concept using machine learning on Earth in order to develop a rapid, consistent, and streamlined method to analyze and interpret data. So here the idea is to send all the data back to Earth, help the scientists on Earth to study and to quickly analyze the data, and support them in the decision-making process. So when I want to explain the science autonomy concept and how this idea was born, I have to describe to you two disciplines. Of course, first, the space science with different domains, with planetary science, astrophysics, earth science, heliophysics, but also the different steps of a space mission. From the launch, of course, the mission operations, the data transmission, and when we get the data, the science analysis. So this is the first discipline that we want to combine with computer science discipline that I think you are more aware of with all artificial intelligence, machine learning, deep learning. So what we want to do here, the idea was to use the state-of-the-art artificial intelligence to demonstrate the potential of interdisciplinary artificial intelligence approaches to tackle the new challenges we have in planetary missions concept and missions. So mainly for real-time operations, for data transmission, and for science analysis. So when I use the term non-robotic science autonomy, it's to refer to the ability of the instrument to analyze its own data on board and to be able to calibrate itself, to optimize the parameters for the next operation, to be able to make mission level decision based on the scientific observation that is made on board, and to determine which data has to be first sent back to Earth. So it's also data prioritization process. So it was kind of new at NASA Goddard, this approach, how to do this, how to implement machine learning in a space mission. So what we did is we tried to pair the researchers. So astronomy, astrophysics, we can think about all type of researcher. So for me, it was planetary science experts and also mass spectrometer experts with machine learning experts, so data analyst, engineer. So because my background is not in research, I had to understand what was the goal of these missions. And we want the researchers to drive the research quality. So we want to be sure that we answer the good scientific questions. So we had researchers working with the machine learning people to work together to be able to develop the right prototypes and the right tools that will help in the analysis of the space data. And by having these interdisciplinary experts, we were able to have different approach and use different theories and methods in order to answer space exploration questions using artificial intelligence tools. So this is a lot of words, this is a lot of theories, and I wanted to give you a more real, concrete example with my main project, in fact, at NASA with the ExoMars mission. So I've been working with Eric Linus, the software lead for MOMA. Maybe he's listening this talk, I hope. So yeah, just to give you an overview, ExoMars mission is a collaboration mission between the European Space Agency, the Russian Space Agency, and NASA. And ExoMars mission will be launched in 2022 in order to search for past or present life on Mars. And it will be really interesting because it will be able to study the subsurface of Mars with a drill that will drill in the surface. And so at NASA Goddard Space Flight Center, we developed this instrument. The quality is really not good, I'm sorry. It's named the MOMA instrument. So it's a Mars Organic Molecule Analyzer instrument that will search for molecular biosignatures that will be able maybe to reveal signs of ancient Martian life. So without going into all the details, I want to explain. We'll have the sample collected on the rover, and then it will be delivered to the instruments. And we will first do one experiment using LDMS. So LDMS is a mode of the mass spectrometer, meaning laser desorption mass spectrometry. And all these data will be sent back to Earth. And when the data will be returned to Earth, all the science team will study the data for 24 to 48 hours. And they will have to decide what they want to do next on the sample. So they will have different options. For instance, they could choose to stay with LDMS mode, but change the parameters, decide to go to another mode of the mass spectrometry named gas chromatography mass spectrometry, or they could decide to change the sample because it was not a good sample and they don't see anything. So because the LDMS and the MOMA operation is planned to have a very short turnaround during Mars operation, the team will need help in their decision-making process. So anything that could make more effective and faster will be beneficial for science planning. So the idea was, can we an algorithm to recognize spectra? And for this, we were really lucky because on the top left corner of this slide, you can see a picture of ETU. So ETU is Engineering Test Unit. It's the same instrument as MOMA, but it's in our lab at NASA. And so we were able these last year samples on the ETU. And so we collected a lot of data and created a database of every mass scan performed on this instrument that is similar to the one we sent on Mars. And because we have this data set, we were able to tag the data set that we collected over the years. And we were able to tag them with the name of the sample. So you can see we tried different samples here, or with the categories. So here we asked the scientists to come with some categories label that are linked to the scientific goals of the mission. And so we were able to have two different ways of labeling, so categories or samples name. So after this, I want to give you an overview of the whole process, the final goal of the project. So the project is we are still working on it, but the idea is we will have 3 steps. The first step will be a pre-processing step. We will receive all the raw data, the mass spectrometry data from Mars, and we want to convert all this data to a machine-readable format. So we reduced all the data set to a 1D array with 2,000 numbers containing all the data from the mass spec, and also several parameters that are used for the LDMS mode. And so our first idea was to identify the good and interesting spectra to the bad spectra. So you can see it's really black or white in my engineering background, but for scientists, it's really more specific. So that's why we had to work with them a lot. So for this, we use a filtering stage using unsupervised machine learning in order to cluster the data. So for instance, we can think of a cluster with calibration data, a cluster for engineering tests, a cluster with low signal, high signal, a cluster we don't know what it is, and we think that the scientists should take a look at this cluster because it's really interesting. And then after having clustered the data, because we don't want the scientists to have a lot of time studying the calibration data, we have the matching stage for the most interesting data. And we use supervised machine learning thanks to the data set that we have and the different labels that we had. And once trained, new samples, so new samples that we will receive from Mars can be used here, and we can predict what is the most similar known scans that can be returned to and the scientists can have all the information about. So in 2018, you run this sample and you decided to do these operations. So just to give them more information about what they did, but no decision-making made on board. So now that I described the whole step, I can tell you more about different tools that we used. And because I think you might all know for artificial intelligence and more for machine learning problem, what is the most important part and the most challenging is to understand the data, the input data set. And so to help us visualize data, we use UMAP. So UMAP is Uniform Manifold Approximation and Projection Algorithm. And it's really, really powerful for a dimension reduction algorithm, but also for other techniques. But just to be brief here, we can use UMAP in an unsupervised way on the left side of the slide, but also on a semi-supervised way with the labels. And what is also really interesting is that we can use this really reduced data set for a pre-processing step for the supervised learning approach, but also we can use, we can have new data coming to this existing embedding space. So we can train a first step here with clustering data, and we can just add more data into this embedding space here. So first we try to understand our data set, of course, and then just to also give you an overview of some results for the unsupervised stage. So the filtering stage was, can we find the most interesting data for the scientists to focus on in the short amount of time that they have, like garbage data and not garbage data. So we try to remove bad spectra from them using some clustering algorithm on sklearn. So basic algorithm, and we develop some workshops with the scientists to show them the different clustering tools that we develop and what was making sense based on the scientific goals, because some algorithms were really effective but were not good for the MOMA goals. So we work with them a lot, and we also develop some visualization tools. So here it's the Xena interface, and you can see some clusters. So here, for instance, in calibration data, here it was another test, I don't even remember what it is, but you can see that different cluster algorithms were trained, and we finalized this approach with one clustering algorithm that was good for the MOMA scientific goal. And then for the machine learning, the supervised part, we wanted to focus for this step on a matching step. So because we had all our data set that was tagged with different labels, either the sample names of the categories, we were able to train different supervised algorithms to identify the categories as well as specific samples. So we first tested different algorithms, classic one, decision tree, random forest, also KNN, some MLP classifier, and then we decided to develop our own neural network to be able to tune it. So we developed two basic models on neural networks with and we performed different tests. So here just one test with two models with the samples name and then the categories name, and you can see different performance metrics such as the accuracy, the R-square, the log loss. So we studied all of these results for our data set. And when we were happy with the model we worked on the hyperparameters tuning. So what is the best number of epochs, what is the best loss functions all this hyperparameterization to have the best performance metrics. And right now, I'm still working on the combination of UMAP and supervised learning. So this is still work in progress, and other visualization tools are still work in progress. But what is interesting is this whole process of classification engine. So from the filtering stage, the matching stage, the aim is to generate a knowledge about the sample. And this knowledge is used after to guide the decision-making process. So just to give you also an overview of what we achieved and what are the next steps. For the data set takes a lot of time to massage the data set, to understand the parameters to use, normalized, everything, but I'm sure you're all aware of this. And also we'll need more data. So we are also working on how to improve our data set to use, for instance, transfer learning, also GANs and autoencoders. So this is a new step we're working on. Then the labeling step was really interesting because we could use UMAP and understand and see our data set, but also be able to use different labels. So a next step could be also to use other labels, maybe operational labels instead of samples or categories. And for the algorithm machine learning, so we use very powerful libraries for unsupervised and supervised learning, and we were happy with the models we developed, and right now we are implementing this on our software tool, but we are still tuning and use UMAP with supervised machine learning to have a data set that is not 2,000 parameters at the beginning, but only a 2-dimension data set. And then we are still working on the visualization tool. So the software development, we have a lot of work for this to work with the scientists to understand how they will operate during Martian operations and to be able to build the decision-making process after. So we are working on the customer also, like it's when we say matching stage, the customer also like refers to in 2018, you run this sample and you decided to do these operations. So we are building this interface right now and work with the scientists to really understand their needs during Martian operations. So I try to be brief on this project, but I have so much to say more. But I also wanted to talk about other projects and challenges. So for other projects, there are projects not only for planetary missions, but for astrobiology purposes. That is a life detection mission. So I put the link here. Feel free to email me if you have questions about this, because I'm also working on this project and it's really, really cool. But I also want to mention some challenges for science autonomy, because we have to develop tools to be able to trust artificial intelligence for very expensive missions that we launch in our solar system. And we also have to put this mission design consideration from the beginning, because right now our team of machine learning people had to work with the science team and use what they already had and try to make something possible. But if they were working from the beginning together, it will be easier. And also the sample set. So our data set was really a lot of work to have a good data set. So if it's possible for the scientists and for the machine learning people to work together from the beginning, it will really help the machine learning work also at the same time. So science autonomy will really enable missions that will not be possible without machine learning. So even if it's a lot of challenges, machine learning will and must play a vital role in the coming age of space exploration, because science autonomy is necessary to achieve science goals for planetary missions under these extreme conditions, under these short mission timeframes, and because of the long delays in communication. So I hope I gave you an overview of how we can use machine learning and artificial intelligence for space missions. And I don't really know how it works, but I'll be really happy to take any questions right now.
That was fantastic, Victoria. We do have a question that I'm seeing in the chat. Can you describe the scale of data you worked with? So the volume, cardinality, dimensionality, and any back-end tooling, example, Ray Spark, required for distributive scale, and any bottlenecks that were noteworthy?
Yeah, so that's a good question. I could not, of course, put the data we use because of NASA confidentiality, but we can give you an idea. So the sample we use, I said, from the ETU were only the LDMS mode, so only one mode from the ETU, so in engineering test unit. And from this, we had maybe 500,000 spectra. But a lot of spectra for this instrument are used for engineering tests, electrical tests, mechanical tests. So it's not only for scientific data, scientific purposes. So because of this, we have to clean our data set and use only the scientific experiments made on the ETU. And we finished, unfortunately, with only 30,000 spectra at the end. So it's really not that much for scientific, for machine learning purposes, and even more because a lot of these tests were made with calibration data. And the calibration sample that we use, I mean, for scientific goals, we don't really care about it because we already know what it is, and our goal for going to explore Mars or other missions is to detect something else. So we don't want to only have a data set with calibration data. So we had to remove a lot of sample of calibration data. And then the second part, how was the data? So the data is a mass spectra. So it just plot with the x-axis is mass, we can say kind of mass, and the y-axis is abundances. And so you can have a spectra with, like, for instance, mass 300, high abundance. It just say that your molecule has the mass of 300. It's really simplified. So we decided to have one D array with parameters from 0 to 2000. And at the end of this 2000 array, we put 7 more parameters that are linked to the LDMS spectra, LDMS method. So for instance, the laser, so we use a laser. So the laser energy, the number of laser shots that we do, and 5 other parameters that are more technical. So yeah, I think I answered 30,000, that was the question, and the data set is a 1D array plus 7 parameters.
Mm-hmm. Great. Wow, well, I can't wait to hear more about the success of these missions in the future.
Thank you.
Thank you so much for being here.